to speak in the RA seminar. Um, so I have to apologize. I think my abstract, as usual, is more aspirational than what I actually was able to put in the talk. But I will try to narrate the general what the general role is of the GGH, the Generalized Generating Hypothesis, and I will mostly concentrate on one example of the generalized generating hypothesis, but it will appear I will actually define it at some point. Um, but I won't talk about all of its many sort of manifestations. So I will talk about it really here more in the context of ring theory. So in the exact category of R modules. In the paper, which I'll show you later, is actually quite technical. I'll show you it's kind of just even visually very technical. So I will maybe give you a little bit of a glimpse of what the arguments look like. But actually, what's nice is though it's very quite technical, we can prove I think one important consequence of this theory. And so what I'd like to do is I'd like to talk in the category of R modules. Um, and later on, when we get to the appropriate place, I'll explain how if we work in the exact category of complexes, how this is related to some other theories. Mostly, actually, this is meant to be a unification of the theory of the terminology ghost morphism. So there's many terminologies of what it means to be a ghost morphism in modular group representations and in the setting of the derived category of a ring. But I'll get to that in a minute. But I will explain more what it is in the sort of concrete classical setting of R modules. So the first theorem that we're going to try to dualize. So we're going to prove a theorem, which is the dual of a theorem of Shu. And he proved that if you have, if the pure injective modules in the category of R modules are closed under extension, then every cotorsion module is pure injective. Okay, so this is like an important thing. And what we're going to do is we're going to prove the dual theorem. So let me first explain the terminology that's being used here and how it's, I mean, I imagine most of us already know these things. I know you know these things. I just want to describe it in a certain way that we can then dualize and discuss further. So if you remember, we first have a notion of X orthogonality for subcategories of the module category. So if you have and this is really the classical, this has to do with the classical approximation theory. And so if you have a subcategory C of the category of modules, then we have the left perp of C. So these are all the modules that are left orthogonal to every module in C in the subcategory C, and then we have the right perp of this subcategory. So this is all the things that are right X orthogonal to C. And the reason why this is interesting is usually the first example that, at least to me, arises is that if we start with the category of pure injective modules, let me look at this first example. If we start with the category of pure injective modules, and we look at the left perp, we get the subcategory of flat modules. And then if we define the cotorsion modules to be the right perp of the flat modules, then the cotorsion modules become a category that contains the pure injectives. So from here, we see that every pure injective module is cotorsion. But the nice thing about the cotorsion modules is that it's a homologically defined subcategory. It's right X orthogonal to some subcategory of modules, namely the flat ones. And then it turns out that this is so by a cotorsion pair, what we mean is a maximal pair of subcategories that is X orthogonal to each other. So this is the sort of, I would say, the most important um, cotorsion pair. I always, whenever I see a cotorsion pair, I somehow compare it always with this one. So on the left, you have the subcategory of flat modules, and on the right, you have the subcategory of cotorsion modules. And this is the cotorsion pair. We would say that it is co-generated by the pure injectives, because we really started with the pure injectives, even though we don't see them there. We started with the pure injectives. We took the left perp and we got the left category R flat, and then we took the right perp and we got the category of cotorsion modules. So this is a cotorsion pair, and it was the sort of subject of a very important conjecture, the flat cover conjecture, whether this is a complete cotorsion pair. So this was proved by Bitan, El-Bashir, and Enox, I think around 2001. And so and complete means that basically a cotorsion pair is complete if it satisfies Salce's lemma. What does Salce's lemma mean? State. It says that if you have a module, so if I start, so if I start here with a module, then it lies at the right end of a short exact sequence where this is flat and this is cotorsion. And then this gives us a very nice, like, concrete way of then F is a pre-cover of M. And the reason is because, you see, if I let me just move this down a little bit. Because if I take any other flat module here, then when I take the pullback, it splits, because you have here C, and then it splits, and therefore, because the flat modules and the cotorsion modules are X orthogonal, the pullback splits, and that gives me a factorization from any flat module, from a morphism from a flat module to M through this what's called a special. This is what's called a special flat precover. And then Salce proved that when you have a cotorsion pair, that if we have special precovers, if and only if we have special pre-envelopes, which is the exact dual role. So this is very nice, because usually, as you will see, and this talk is an example of it. The results of this talk is we can always dualize things. Whenever we do this kind of categorical formalism, there's always the dual. And so there's always, whatever concept we define, we can always define the dual concept. But very often the existence uh, doesn't give the same status. So for example, you know how in the category of modules, we always have injective envelopes, but not necessarily projective covers. So from the status of existence, they don't have the same, the dual object doesn't have status. But Salcha's lemma is one of those very nice results where you do have the existence of dual objects. And so this is a very important. And that's what it means to be complete. So that means Salcha's lemma. And I don't want to go too much into these things. I imagine most people are familiar with this. So Schu's theorem can follow very quickly. So you see, we have these nice because of the flat cover conjecture. We have these nice special precovers and flat precovers and flat cotorsion. But remember, let's go back to the original subcategory of pure injectives, which co-generated this cotorsion pair. Well, we know we have pure injective envelopes, but we don't have any kind of sort of status, kind of homological explanation for these, for them. In fact, that's not necessarily a bad thing, but it's just, I'm just making the point. It's just an observation. Now, in this case, how do we see Schu's theorem? It follows from Wakamatsu's lemma, which states that if you have a subcategory closed under extension, and every module has a cover, then it is special. Okay, I just realized I should have said the dual of Wakamatsu's lemma, that if every, I should have said here, envelope, then M is special. And so it should be this. And so then it turns out that the envelope is special. In other words, that the co-kernel lies in the left perp of the enveloping subcategory. So if we assume that if we take our subcategory to be the category of pure injectives, and then the hypothesis of Schu's theorem is that the pure injectives are closed under extensions, then we can apply, because the existence of pure injective envelopes, and if we assume that they're closed under extensions, then we get that the pure injective envelopes are special. In other words, that the co-kernel belongs to the left perp of this of the category of pure injectives, which we know, if you remember, is flat. So what we said earlier was that the left perp of the pure injectives in this case is flat. So that gives us a so it says that every pure injective envelope is special. And so, for example, we get that we get this following thing, that we can apply this to the subcategory of pure injective modules. And so in particular, if M is a cotorsion module, we look at its pure injective envelope. The co-kernel is flat. And because cotorsion envelopes and, cotorsion modules and flat modules are X orthogonal, it splits. So then M is a summand of a pure injective, and therefore it is itself pure injective. So this is how the Schu's theorem follows from Wakamatsu's lemma. And important here is the existence of pure injective envelopes, not just pre-envelopes, but envelopes, and that we have Wakamatsu's lemma. So now we can, and I guess it occurs to me as I was writing this, if to what extent the results, I asked myself, what if the results of what I'm telling you about give us some kind of, actually can be formulated as some kind of weakening of Wakamatsu's lemma, because what we're going to do now is try to dualize everything. We'll look at the dual situation. And so this is the second sort of opposite example, namely, if we start with now the subcategory of pure projective modules, and we look at the right perp, then of course we know that every finitely presented module is pure projective. And we know that, in fact, the pure projectives are just summands of direct sums of finitely presented modules. So it turns out that the right X perp of the pure projectives are just the FP injective modules, also known as absolutely pure. Absolutely pure modules. We're always working in the category of left arm modules. And then we can, just like we introduced the notion of a cotorsion module, it was just a kind of a homologically defined subcategory. We can now talk about the FP projectives. So this is the subcategory of FP projective modules. Then this is defined to be the left perp of the FP injective or absolutely pure, subcategory of absolutely pure modules. And so in this way, we get an entirely dual situation, and we obtain a cotorsion pair again. Now, this time it's generated by the pure projectives. The other cotorsion pair, if you remember, was co-generated by the pure injectives. This one is generated by the pure projectives. And of course, it doesn't appear in the pair. Here I'm talking about this part right here. This cotorsion pair consists on the right subcategory are the absolutely pure FP injective modules, and the left are these this kind of, just again, we don't know it. We don't know what the FP projectives are, but in fact, we know them much better than we understand the cotorsion modules. So it turns out that there is a theory, basically using Ekloff's lemma, and in what we're doing here is actually a generalization. This project that I'm talking about is a kind of generalization of Ekloff's lemma. And Ekloff's lemma can be actually used to describe the structure of FP projective modules. Basically, they are modules that have a filtration, so an increasing sequence of submodules indexed by some ordinal, and each of the quotients is pure projective. So here, things are, again, it looks completely dual, but because thanks to Ekloff's lemma, the classical Ekloff's lemma, we actually understand the FP projective modules much better than we do understand the cotorsion modules, at least in their relationship to the generating or respectively co-generating subset. And so the theorem that I'm going to talk about today is proved with Sergio Estrada, Shanhui Fu, and Sinem Odabasi. Those are my co-authors. And what we're going to prove is that if the subcategory of pure projectives is closed under extension, then every FP projective is pure projective. Okay, so if you can imagine, so here's the problem. We do understand the FP projectives. Every FP projective is a filtration, so a transfinite filtration whose factors are pure projective. And we are assuming that at the first level, so you start with a pure projective. Let me try to, maybe I can write it down a little bit here. If I can show it a little bit. Let me move this down a little bit. So what we have here is a module, and it is filtered. It has this ordinal filtration. So in other words, a continuous increasing sequence of submodules such that each of the factors is belongs to is pure projective. Then if you can understand the problem, well, M2, for example, is an extension of pure projective. So M2 is also pure projective. So we know for all these, so if we assume the hypothesis, then this will also be pure projective because it is an extension of M2 mod M1 by M1, etc. So we know that at all the finite places, at the initial part of the filtration, in fact, these are all pure projective. And so we have to prove it for the limit stages. We have to somehow use the hypothesis to prove it for the limit stages, and then we'll be done. Then we can just proceed by ordinal induction. And then we'll have it. So that's really where the problem is. And also, of course, we cannot dualize Schu's proof because we have the existence of, so this we have again pure projective pre-covers, but we don't have covers. So every module admits is the codomain of a pure epimorphism coming from a pure projective module, and this is a pure projective pre-cover. But we do not have at our disposal, we don't have available covers, so we cannot use that. If we did, then we could apply Wakamatsu's lemma, and we would get the theorem immediately. So now these rings are kind of strange. So what kind of rings are there? Well, notice, so we can ask ourselves, like once we've proved this theorem, we asked ourselves, well, what kind of rings are these where the pure projectives are closed under extension? Well, as a corollary of the theorem, if R is left Noetherian, then we know that absolutely pure is the same as injective. And so in that case, every module is left X orthogonal to the FP injectives. And so our cotorsion theory, cotorsion pair here is trivial. The right subcategory are just the injectives. And it means that every module is FP projective, which is the definite equivalent condition for the ring to be left pure semi-simple. So you can see that what we're talking about here, and in fact we don't know. Well, maybe Shanhui remembers if we know examples of these. If we have examples of such rings, in the dual case, there are some examples where the pure injectives are closed under extension, but not pure semi-simple.
I think von Neumann record ring.
Yeah, von Neumann. Yeah, that's what I thought. Yeah, usually these, it's pure semi-simple or von Neumann regular.
Yeah.
So in that case, similarly, every module is FP projective. Okay, so now we're going to try to generalize this notion to what's called ideal approximation. So approximation theory is this theory of special pre-envelopes and special pre-covers with respect to some subcategory. And ideal approximation theory is the same kind of theory, but with respect to ideals of the category of R modules. And so here you can see the classical theory was developed sort of by two different schools. You have approximation theories mostly devoted to the representation theory of Artin algebras, and that was developed by Auslander and Smalleux, and that works in the category of finitely presented R modules. And then Enochs and Genda proved it, developed this approximation theory for the entire category. And again, I would say the main result is you've seen the two main results of approximation theory are the Salcha's lemma and Wakamatsu's lemma. Those are very, very important. Now, so once we start talking about ideals, let me just remind you quickly what an ideal is. It's a sub-bifunctor of the Hom functor. And that means that for every pair of modules, you have a subgroup of distinguished morphisms that's closed under left and right, pre-composition and post-composition. And the important thing to see here, so I think it's very important to be sensitive to the following thing. If you are in the situation of Auslander and Smalleux, this is like, to be crude, this is like small representation theory, and the other one is big representation theory. And for example, if you're working in a small category, or skeletally small category, like Auslander and Smalleux, then it's fantastic because your ideals form a lattice, and you could talk about this lattice. You can do many, many things with this lattice. If you're in the big category, you kind of run into immediately you run into a foundational problem because An ideal is really a class. It's a map between pairs of modules uh, to abelian groups. And so it itself is a class function. And so if you want to talk about the lattice of all ideals, it's even worse because you're talking about a class of classes. So you have to be very, very careful in terms of, running into some logical paradoxes when you're working with things that we're very used to. Of course, we're in a ring, we regularly talk about lattice of ideals without any problem, right? So sometimes you have to be a little bit careful when you go to into the big category. Um, and so the important examples are the standard example. The first example that you see is that if you have a subcategory of modules, then you can look at the ideal of morphisms that factor through one of these objects. Um, the only thing that you should remember is that, for example, like in a ring, yeah, okay, no, never mind. That's all I wanted to say. And then here is something interesting is that given two ideals, we can do the usual thing. We have the lattice theoretical infimum and supremum operations. They're commutative. And then we have a non-commutative. We can multiply two ideals in the sense of Dedekind. Um, and that's just it turns out that if our category is additive, like our mod is, then this is actually the category of compositions. You don't have to say generated by composition. It really is. And we call an ideal idempotent if I squared is equal to I. And of course, every example one, the category of morphisms that factor, the ideal of morphisms that factor through some category will always be idempotent. And sort of one important question that arises is the converse. When is an idempotent ideal an object ideal? For example, a classical situation is if we look at the skeletally small category of finitely generated projectives, then an ideal is actually just completely determined by its R component, which is an ideal of the ring. So the ideals of this category are just the ideals of the two-sided ideals of the ring. And then the question of whether an idempotent ideal is an object ideal has to do with when you take in a ring, when you have an idempotent ideal, whether it's the trace of a projective module or whether it's a trace of a finitely generated projective module and things like that. So this is actually quite related to some very classical questions, this thing. And so now what we're going to do is we're going to kind of show you how the theory generalizes, how the classical theory generalizes, and it's actually it looks like the results look very similar to the classical. So it's the proofs are entirely different, but the theory is very closely in analogy to the classical theory. So I'll develop it that way, especially in hindsight. Again, there's kind of a main example. So a morphism is called a phantom if Tor blank phi, so this is right, so I'm talking right here. This phantom here. If Tor blank phi is 0. In other words, this a phantom morphism is basically like the morphism version of a flat module. Okay. And what we want to do, and these form an ideal. And so what we want to do is we want to replicate the whole classical theory, but now for ideals. And the dual notion is called a cophantom, but in our paper we introduce a general theory of ghost morphisms. And so this is also, let me just mention that this is also cophantoms. It's the dual notion. And these are like the morphism versions of absolutely pure uh, modules, FP injective modules, because they're defined to be precisely the morphisms that are right X orthogonal to the FP for the finitely presented modules. And so in general, we have this notion of S ghosts, and if the category, if it's a morphism which is right X orthogonal to some subcategory of modules. Now, in the paper, we work in much greater generality. We work with exact categories, and we work in and sometimes we work in category of modules, as I'm doing here, but we also work in the category of the exact category of chain complexes. And in this case, we're able to show that, for example, in modular representation theory of groups, we have something called a ghost. A morphism is a ghost if the Tate cohomology vanishes on it. And in that case, we show that it is of this form. In other words, there is a subcategory of the category of complexes such that the ghosts, the morphisms traditionally known as ghosts, there are S ghosts for some subcategory. And similarly, in the work of Hovey, Lockridge, really Lockridge, he considered ghosts in the derived category of a ring. And there we can also show, it's not difficult, but it kind of ties everything together, that these are really the morphisms that are right X orthogonal to a certain very nice class of very nice class of complexes. And so so this notion of S ghost really unifies and subsumes all the known uses of this terminology, both in the derived category and in the modular representation theory. But here in this special case, we're interested in this kind of classical dual of some concepts that arise in the approximation theory. So now, what does it mean to be X orthogonal? What does it mean for two ideals to be X orthogonal? Well, so here's so this is kind of complicated to explain. So I want to do it a kind of slowly. And suppose I have two morphisms, F and G. So here I have F and I have two morphisms. And if I have a map from B to X, H, then I can precompose it with F, or I can postcompose it with G. And the order doesn't matter. And that's this. So this sends H here down to GHF. Okay. And the commutative diagram says that it doesn't matter whether I precompose with F or postcompose with G. And it's obvious, at least to me that this is commuted, doesn't matter, the order doesn't matter. And so, oh, by the way, note, and this is kind of important in some recent work with that Shanhui and I are doing with Hongyu Zhu and Kevin Schlegel. And so there's also a notion of um, a zero-dimensional approximation theory. So it turns out that two morphisms are going to be Hom orthogonal if and only if the ideals that they generate are actually Hom orthogonal. So this is not important here. But now if we do the derived version of this, okay, so the derived version says that the following, and I think it took us so it says we have the same diagram. We have two morphisms, one from F from A to B and G from X to Y. And we have the same exact sort of a one-dimensional first derived version of that um, commutative diagram above. But it took us quite a while uh, to comprehend that, in fact, this is commutative. This is kind of the fact that this diagram is commutative follows from the definition of X, of a bifunctor. But still, I think it's not, I really do think it's non-trivial that if we start with this, let's say we start here with this short exact sequence, and if we take the pullback along F and then the push out along G, that the sigma, this sigma that we get here, whether we take first the pullback along F and the push out along G, or push out along G and then pull back along F, we get the same, we get equivalent extension from A to Y. And no, as we were working on this, it took us quite a bit to accept that this was actually, it's just like a proof by definition, but it's a really non-trivial proof by definition. And so now if we go back and we try to do the whole thing, um, if we try to do the whole thing, but now with respect to ideals. So we take the ideal generated by the pure injective modules, and we look at the left X perp of that ideal. We get the phantom. So this is the phantom ideal. And the whole point, the whole advantage of the ideal, looking at things in the ideal point of view, is that if we now, if you remember in the classical case, the left perp of the pure injectives were the flat modules. And here they are the morphisms, the sort of the flat morphisms. And then when we looked at the right perp of flat modules, we got this much, much bigger category of cotorsion modules. What's nice about the ideal point of view is that when we look at the right perp of the phantom ideal, we get, again, an ideal generated by some subcategory, but it's very, very, it's as small as it could possibly be. It contains the pure injectives, but it's the objects are just extensions of injectings by pure injectives. So we know that the right ideal has to contain these objects, but it turns out that it is exactly the ideal generated by these objects. And so this is also a complete theory. And so what does it mean to be complete now for a cotorsion pair of ideals? So again, this is Salce's lemma. So this is going to involve the ideal. Salce's lemma. And here, what we get is this notion of a precover, a special precover is gotten by, if we take a left module, then a special I precover is going to be a left triangle in the stable category modulo projectives. So it looks like something like this. It's a it's a so the precover is this map I. So I is a morphism in M. Sorry, in the ideal I, and it arises as the push out along a morphism in J from the syzygy of M. And then it turns out we have the dual notion where here, J, this is the J pre-envelope right here. It arises, this is a right triangle. It, it's a sequence really of three morphisms, which is a right triangle in the stable category modulo injectives. And it turns out that Salcha's lemma holds here. It's actually a nice, like you have to work in a three-dimensional commutative diagram to prove this. And it turns out that the ideal Salcha's lemma also holds true. And this is the ideal Salcha's lemma, and this was proved again by Fu Gilasencio, myself, and Blas Torresias. So this was sort of the first result of ideal approximation theory, was a kind of analog of the main result in the classical approximation theory. And then every module turns out to have a special I precover if and only if it has a special J preenvelope. This is the definition of complete. And because of the theory, it makes sense. The definition makes sense. Now, again, it turns out we have the dual as well. So if we look at the here, if we take the if we look at the category of pure projectives and look at the ideal generated by the pure projectives, then we look at the right X perp, then we get the FP ghosts, the cophantoms. But as same as above, the theory dualizes, and so that the left perp of the ideal of cophantoms, or as we call them in this paper, the FP ghosts, again, it's the same thing. It's an ideal generated by a subcategory which is just a little bit bigger than the subcategory of pure projectives. And indeed, it's just, again, the dual result. It's the subcategory of pure projective by projective modules. And again, this is complete. So the ideal Salcha's lemma holds for this category. And so now here comes the part where we're going to sort of go into what we're proving here. Shanhui and I proved that, if you remember, I showed you that ideals are closed under three operations: the sum and the intersection, the lattice, and also multiplication. So using composition of morphisms, ideals are also closed under multiplication. It turns out that there's a fourth very interesting operation, and it is called the extension of two ideals. So if we have two complete ideal cotorsion pairs, then it turns out that, so that means what? That means that the I sub 1 and I sub 2 are special pre-covering, and the J1 and J2 are special pre-enveloping. And it turns out that this nice notion of special approximation is closed under multiplication of ideals. But to prove it, one has to sort of see that has to characterize the orthogonal ideals. And so it turns out when you multiply the two special pre-covering ideals, the right per X perp is this extension ideal. And here's how it looks. So it looks like the set of all morphisms. So the morphisms of the extension look like this. They are morphisms from X to Y that factor through a short exact sequence where J2 belongs to J2 and J1 belongs to the ideal J1. And it turns out that this is the right X orthogonal of the, and of course, just like if you look at the product of two ideals, we know that this is contained in the intersection. And this extension ideal contains the supremum J1 plus J2, the commutative lattice theoretic operations are related. And also, of course, this one is complete. And now, here's the thing is now going back to our to the ideal to the complete ideal cotorsion pair generated by the pure projective modules, if the pure projective modules are closed under extension, this is equivalent to the question, to the statement that the ghost ideal is idempotent, okay? And what we want to prove, the dual of Schu's theorem will, it turns out it will follow, I will explain in a minute, if we can prove that this psi is an object ideal. In other words, if it's the ideal of morphisms that factor through a, by the way, I'm pretty close. Do I have, I forgot to ask, is it 50 minutes or an hour?
Oh, no problem.
Sorry?
5 minutes you have time.
Okay, thank you.
Yeah.
And so it turns out that we, in this paper, we generalized this, we have a transfinite generalization where we introduce a kind of transfinite product of ideals. And we prove that we prove that the entire filtration, if J is a special pre-covering ideal, then all of the ordinal, these are called inductive powers of J, then all of these are themselves special pre-covering. And there's a lot of interesting questions that one can ask about this this filtration and about the convergence of this filtration. And with all the definitions of phantom, of ghost, I mean, the lambda generalized generating hypothesis for S is the statement about whether this filtration converges. So this here is it all contains the objects. The objects contained in the ideal are just the identity the objects are the modules for which the ideal contains the identity morphism. And this is always going to be contained it's going to be a lower bound for this filtration of inductive powers. And the question is, does it converge? Is there a lambda such that some lambdath inductive power of J is an object ideal. And so it turns out that we prove that these ordinals are actually let me see, this is then for every ordinal. This is not exactly correct. This is what I wanted to say was that the orthogonal that the left orthogonal here of all the filtrations in S. And here, what we're going to use is the fact that, so Enox and Stovicek proved that if we have anything that is filtration by finite, by pure projectives is actually can be expressed as an omega filtration by pure injectives. So here, when this is true for when S is equal to R, pure projective. And now we also proved that if, so this is our theorem that I forgot to mention, that if psi is idempotent, then all of the inductive powers are also equal to psi. And when we go to using the Stovicek-Enox theorem, we can prove that psi omega is equal to psi, and that this is a sorry, and that the right perp is the category of FP projectives, and so this implies FP projectives, and so this will imply that no, I think let me try to remember. Yeah, and this will imply that the that because this is equal to okay, so somehow I'm a little bit confused, but these are the three main ingredients of the proof is the existence of this filtration of approximating ideals, the Enox-Chowicek bound, and the fact that but the assumption of the dual of Schu's theorem implies that the filtration is actually constant. And because it converges at omega, it turns out to be an object ideal. Okay, so I'll stop there. Thank you for your attention.
Thank you very much for your very nice talk. Are there any questions or comments?
I have a question.
Oh, hi, Diego.
Yes, please.
Hi, Ivo. Nice to see you. So as far as I understand, I mean, in a bit of more general context of extriangulated categories, Salcho's lemma still works as long as you have enough E projectives and enough E injectives. So I was just wondering if, in order to prove the ideal version of Salcho's lemma, you also need to, or maybe you implicitly are using that there are enough projective morphisms and enough injective morphisms in this case. And if so, if it could be generalized to other ideal categories, let's say.
Yeah, we have yeah, in a paper that will appear very soon with Shanhui and the other two authors that I mentioned, we have a kind of zero-dimensional Salches lemma. And it also gives a condition for the so the ideal homorthogonal to a product of ideals is also going to be a similar kind of extension of ideals. And yeah, I think we hold it, it will hold for some for X triangulated categories, but it's a little bit different. It's more like a zero-dimensional version of ideal approximation theory.
Thank you.
Hmm.
Any other question or comments?
Sorry, I also had another question that I forgot.
Mhm.
Is there any ideal version of Wakamatsu's lemma?
There is. Thank you for asking that question. There is an ideal version of Wakamatsu's lemma, and it was the main sort of goal of our work when Shanhui and I proved this theorem. Trying to formulate Wakamatsu's lemma was our main goal of developing the next step in the theory. And in the end, the theory that we developed, actually, we used it to settle a conjecture, the Benson-Yakaja conjecture for finite groups. But the theorem, the Wakamatsu's ideal Wakamatsu's lemma, which was sort of our goal, really never had any ironically never had any consequences. It was just, but it was very useful just as a theoretical sort of objective. Yeah.
Thank you. In that case, could you go back a little bit to when you define like the R flat modules, the first orthogonality relations that you showed in the
Yeah.
classical.
Yeah. Here.
Uh, yeah, precisely. There we go. Okay, so uh, okay, never mind. I was thinking of something, but it doesn't quite work with the example you have here. But thank you for for the anecdote on Wakamatsu's ideal.
Yeah. Yeah. It was a nice irony.
Oh no, actually, sorry, I do have a comment, further comment.
Mhm.
So here you have the flats. So this cotorsion, no, I'm sorry, this cotorsion pair is generated by it's co-generated by the pure injectives, right?
Right.
But then you're using that all modules have a pure injective envelope a bit further down to apply Salch's lemma.
Yeah. Right. Right.
Um, okay, yeah, then never mind, sorry.
Yeah. So it's if you have flat covers, then Wakamat, because flats modules are closed under extension, the existence of it proves that every flat cover is special flat cover, that the kernel is cotorsion. But that's not that's not the sequence in which things were proved.
I see. What I was thinking is that when Salch's lemma applies, for example, in an X triangulated category with enough projectives and injectives, then whenever you have some class and also Wakamatsu's lemma applies, then if you ever have some class such that its right X orthogonal class is, for example, enveloping, then as a corollary, you get that the cotorsion pair this class generates is complete. And also dually, I mean, the dual still holds. So
Right,
that could
right.
be a consequence of the ideal version of Wakamatsu's lemma, maybe.
Yeah. Right, right, right. Yes. That's right. Yeah, thanks. Thank you for that comment.
You're welcome. Thanks for the talk.
So, is there any more question or comments? If not the case, thanks again, Ivo. Thank you very much.
Well, it was my pleasure.